So to illustrate the concepts of streamlines, pathlines, and streaklines, we will look at a specific example. And this is the example of unsteady 2D near surface flow that is typical of long wavelength water waves. So the velocity field is given by two components, u and v, and both components depend on space and time, and they take these particular forms. U is omega psi 0 cos omega t, and v is omega psi 0 sine omega t. And our task is to find the streamline, pathline, and streakline that go through the origin at a time t equals t dash. So let's start with the streamline. We learned earlier that dy dx is u over v, and if you plug in your expression for u and v, you get tan omega, and we're interested at time t dash, so it's omega t dash. We can integrate this so that we get y is the integral of dy dx dx, which is just x tan omega t dash plus a constant. Yeah, so we've just integrated this equation, and since tan omega t dash doesn't depend on x, we just get this one x dependence on the integration, and then we also get a constant. We find the constant by applying the boundary condition, so y at t equal t dash has to be 0, since we're interested in the case that goes through the origin at t equals t0. And so we find that our constant has to be 0. So y is just x tan omega t dash. That is now our equation for the streamline that passes through the origin at t equals t dash. So we can draw this. So it's linear with x, y equals x, and we can find the angle theta here by considering dx dy, and we know that dy over dx is tan theta, and so comparing this with our equation here, we realize theta is omega t dash. So we have found our equation for the streamline and also illustrated the streamline here. Next, we look at the path line. Now the path line, as we know, is given by r, which can be in parametric representation written as x of t and y of t. And we know that dx dt is u and dy dt is v. So this is all we need to find the path line. We can integrate both equations with respect to t. Integrate with respect to t, and we find x equals psi 0 sine omega t plus x0, and y equals minus psi cos omega t plus y0. Now, how do we find the constants of integration, x0 and y0? Well, we know that x and y have to be 0 when t is t dash. That was determined by the question given, and so therefore x0 is minus psi 0 sine omega t dash, and y0 is psi 0 cos omega t dash. So we plug our expressions for x0 and y0 back into our equations for x and y, and we get x equals psi 0 sine omega t minus sine omega t dash, and y equals psi 0 cos omega t minus cos omega t dash. There's a minus in front of this. Now, in order to find the path line that we want to draw, we square and add these two equations, and we're left with x plus psi 0 sine omega t dash squared plus y minus psi 0 cos omega t dash squared is psi 0 squared times sine squared omega t plus cos squared omega t. But this, we know from trigonometry, is just equal to 1. So we're just left with psi 0 squared. And if you look at this equation, you realize that this is simply the equation of a circle with radius psi 0 and a center at the location minus psi 0 sine omega t dash. That's the x-coordinate of your circle, and the y-coordinate is psi 0 cos omega t dash. And we've shown earlier for the streamline that omega t dash is simply our angle theta. So let's draw our path line on the next page. So remember, our streamline was this straight line where the angle of inclination here was theta. Now, our new path line has a location minus psi 0 sine theta in the x direction and plus psi 0 cos theta in the y direction. And that means that this angle here is also theta. So there's a right angle between the location of the center of the circle and the straight line describing the streamline. And the distance of this line here is the radius psi 0. So the path line of the particle that goes through the origin at t equals t dash looks as follows.